Hello, my name is Sean O'Leary from the University of Texas Medical Branch. Today, I'll be presenting our study titled Integrating Data Across Oscillatory Power Bands Predicts a Seizure Onset Zone in Focal Epilepsies. Drug resistant epilepsy affects roughly one-third of patients with epilepsy. For these individuals, surgical resection or ablation of the epileptogenic zone offers the highest chance of seizure freedom. Intracranial EEG plays a central role in localizing this zone, but interpretation is challenging due to complex, time varying spectral activity and heterogeneity in seizure onset patterns. Seizure onset is rarely defined by a single frequency, but rather by coordinated changes across slow and fast oscillations. Using spectral decomposition, intracranial EEG signals can be represented across delta, theta, alpha, beta, gamma, and high gamma frequency bands. Existing computational approaches often focus on narrow biomarkers such as high frequency oscillations, direct current shifts, or ratios of fast to slow power. At the same time, seizure onset patterns vary widely. Approximately 80% of focal epilepsies demonstrate fast, low voltage onset patterns, while the remaining 20% exhibit slower rhythmic or delta brush onsets. This variability motivates a unified approach that can adapt across seizure types while remaining biologically interpretable. Our objectives were therefore threefold. First, to develop an interpretable machine learning model that integrates temporal spectral power across all frequency bands to identify the epileptogenic zone. Second, to predict postoperative seizure freedom based on proposed resections. And third, to implement this framework as an open source clinical tool within the RAVE ecosystem. We analyzed intracranial EEG recordings from 21 patients undergoing epilepsy surgery. 14 patients achieved postoperative seizure freedom, providing outcome validated ground truth, while 7 non seizure free patients served as a held out test cohort. In patients who became seizure free, electrodes within the seizure onset zone demonstrated significantly higher power in the alpha, beta, gamma, and high gamma bands during the first 20 seconds after seizure onset. In contrast, this pattern was not observed in the non-seizure free patients who instead exhibited significantly lower gamma and high gamma power within the seizure onset zone during the early ictal period when compared to the non-seizure free patients. Together, these findings suggest that the magnitude of spectral power carries clinically meaningful information that can be leveraged by more sophisticated modeling approaches. To capture these relationships, we developed a stacked random forest ensemble or SRV electrode model. Individual random forest models were first trained for each frequency band using time-resolved power features. These models were then integrated by an ensemble meta-learner that adaptively weighted each band based on its predictive value, preserving interpretability while capturing cross-frequency interactions. For seizure onset zone electrode identification, the SRV electrode model achieved an overall accuracy of 82%. Importantly, positive predictive value was 96.6% with a high specificity prioritizing clinically safe labeling. Beta, high gamma, and delta bands contributed most strongly to the final model. Interrogating the model revealed a dynamic temporal spectral fingerprint of seizure onset. Early delta and high gamma activity transitioned to sustained gamma dominance, followed by later involvement of theta, alpha, and beta bands. This pattern closely mirrors the epileptogenic zone fingerprint previously described by Granenko and colleagues. A second SRV model, SRV outcome, was trained to predict surgical outcome based on planned resections. This model achieved 95.2% accuracy with strong sensitivity and specificity. Together, this framework integrates naturally into clinical workflow. Intracranial EEG data from phase 2 monitoring are first used to localize seizure onset zone electrodes through SRV electrode predictions. These predictions then inform surgical planning, accounting for anatomical constraints and eloquent cortex. Finally, the proposed resection can be used to estimate the likelihood of postoperative seizure freedom through SRV outcome, informing both clinicians and patients. All analyses are implemented in the open source Freeze module within the RAVE platform, enabling reproducible visualization and clinical translation. Scanning the QR code links to our lab website, including the live demo, source code, and a downloadable Docker image for use on local data. In summary, we present an interpretable multi-band machine learning framework that improves seizure onset zone localization and surgical outcome prediction. Thank you.